Alright, so now we're going to look at how we remove something from a given index, any other index. Alright? So we know that we're not going to be manipulating with heads or tails, but we are going to do the same thing where we're going to get the node before the node item we'd like to remove. Okay, so we'll go ahead and create a before. We could also just go directly to the one we want to remove, but out of just the habit, I like to get the one beforehand, since that's what works for a singly linked list, and I don't like getting confused by having two ways to do something like that. So node E is equal to get node at index -1. Let's go ahead, and I need to give it a name before, so that's what this does, slaps that label onto that guy. We want to remove this node from the list. Alright, so what do we need to do that? Well, that means that I need to make sure that none of these pointers are pointing to him. Okay? Which means that this pointer needs to be pointing over here, and this pointer needs to be pointing this over here. This needs to point over here. This needs to point over here. Okay, so again, we're going to answer our questions by just simply asking what is this one and what is this one. Oh, and right, we definitely want to make sure we get the item we are removing first. So removed. So what is this node? We want to get the item from it. It is before.next. Remove is equal to before.next.item. Awesome. Next thing we need to do is grab. Manipulate these pointers. Okay? So, and it doesn't really matter what order we do them in, because the advantage of being doubly linked is that we've got other ways to do this. So I'm going to say, what is this pointer first? Well, this pointer is before.next. So we need to set it up. Before.next is equal to what? Well, it's going to be equal to this node, which is before.next.next. Just like we did when we were removing the node in a singly linked list. This guy is before.next.next. Okay. Now we need to remove this arrow, and the topology and the way this layout has changed. Right? We need to remove this arrow, but saying before.next to get to this node doesn't work anymore. Instead, I+1 is now before.next. Okay? So now we keep this in mind. What is this arrow? Well, this arrow belongs to this node, which is before.next. That's the memory location it's stored. So the memory location of this node is stored in before.next. And this arrow is referenced by utilizing before.next.previous. So we get that by calling before.next.prev is equal to what? What does this need to point to? It needs to point here, which is before. Okay, so now we go ahead and delete, because there's nothing pointed to him, and then these arrows will go away. And now we need to test that out. We're going to go ahead and add a add. So l.add a C over here. And what I'm going to do now is that I'm going to now remove index 1, remove index 0, remove index 0 again. So I'm going to remove all the items from the list and print out L. So go forward. So we have A, B, C. Remove the B first, which was in the middle. Then we remove A. Then we remove C, which was the last item completely. And so we end up with an empty list. So that's it for a doubly linked list. The get and set methods work exactly the same. So we can quickly do a big O analysis. Guess what? It's exactly the same as a singly linked list. The only difference is that we now have a tail pointer, so now we can since we're keeping track of the tail, we can add to the tail in constant time, because as you can see, that adding to a tail takes constant time since it's the same commands no matter how big the list is. And adding a new head, again, that's constant time just like before. And adding the very first item, that's just setting up 2 memory locations, so that's also constant time. So the linked list runtime has not changed in the slightest.